Hello, this is day 6 from chapter 11A. This is when we start getting into exponential growth and decay, like actual kind of what the function looks like of an exponential function. So if you had a situation where, some population is growing over time, and it goes, at time 0, so at the beginning there's an initial amount of 25, whatever, ants or whatever we're thinking of. And as time goes by, incrementally up by 1, we see what happens in the population is that it goes to from 25 to 50, 50 to 100, 100 to 200, and we could look at that and intuitively see that it's doubling each time. So we could continue on that path and see that this would be 400 and this would be 800. So it's doubling each time. That is exponential growth. Anytime you double something or have something over time incrementally, that would be an exponential situation. So maybe you had at time 0 you had 800, and then as time incrementally goes up by 1, it goes down to 400, then 200. You can see it's being halved each time. So this would be 100, and at time 4 this would be 50. Essentially, there's a formula for that where in a graph it would be y equals a times b to the x, where a and b are constants, are just numbers, and x is the exponent, and that's our independent variable. It's what we input to see what our you would input time there, for instance, to see what your total population is at that time. So a is your initial amount, and b is what we're going to call the multiplier. And we call it that because it has an exponent, and an exponent is repeated multiplication. So it's telling us how many times we're multiplying our initial amount by. And then there's two situations, one where your multiplier is greater than 1. So this would be a growth situation, just like up here. Our b was 2 in that case. And in that case, our formula would look like initial amount was 25, so that's a. And then our multiplier was doubling each time, so this would be 2. And then to the x. So any x you plugged in here, like 4, it would give us 400. If I plugged in 0, 2 to the 0 is 1, times 25 is 25. So this formula works for that. And then if we had our multiplier between 0 and 1, this would be what we call a decay situation, where over time the population or the amount is getting smaller over time, and that would look like this situation. And since each next value is half of the previous, you have your initial value of 800, and then it would be 1/2 or 0.5 to the x. So if I plugged in, let's say 4 for x, I would end up getting 50 for an answer. If I plugged in 0 for x, that's the initial value, 0.5 to the 0 power is 1, 800 times 1 is 800. So this is the basic exponential growth and decay formula. Basic. All right, and then we have another situation where this is an exponential growth and decay, and then we're given a rate of growth. So not necessarily like double or triple or halved like the previous basic exponential growth and decay. R is typically a percent or some value that's a rate of growth or decay per the time period. And this formula may look kind of new. N is your final amount. I'll write some of this down. Our final amount. N naught, or n sub 0, is our initial amount, your starting amount, just like before, where we had a before. And then 1 is 1, obviously, in parentheses, plus r is our rate. And then t is a unit of time, or number of time periods that happen. Now I want to compare this to something that we had learned before, last year mainly, is that this is the same formula as A equals A, your final amount, equals P, your principal or initial amount, 1 plus R to the T power. These are the same formula. We just call them different variables. And this one specifically, when we have P for principal, it's kind of insinuating that we are using money, or a loan or an investment. And the rate would be your interest rate, time still being time, usually in years, and A, your final amount. So these are the same formula. I just don't want that to be a point of confusion. And I can do this. Where P is N naught and A is N. Those are the same things. And then we have compound interest. This actually appears in day 7. So this will be covered again. But the only new thing here, notice the similarities between these two. The only difference is that R in the parentheses is divided by N, and T in the exponent spot is being multiplied by N. And this is again explained in the day 7 video. But briefly, what is happening is, let's say, you had money in an account and they give you annual interest. So they calculate your interest one time a year. And so your balance is going to change once they calculate the interest, and then it'll stay that way until they calculate the interest again off of your newer amount, your current amount, and so on. When you have an N, this is compound interest. What it's saying is, well, how many times a year are we going to compound it? And maybe if N is 2, that's like 2 times a year, so biannually. It basically would be dividing your rate by 2, but then also multiplying the amount of time that's gone by 2. Because say if T was 1 year and it was biannually and would be 2, it would happen twice in that year. But your rate would also be cut in half, be divided by 2 each time it compounds. So really the only new thing here, and this again is touched on more in day 7 as well, the new thing here is the N. It's the only difference between these two formulas. Okay, so a car depreciates, that's a keyword, 20% per year. If the car originally cost $20,000, find the value of the car at the end of 2 years. Okay, so one thing that we know right now is it's changing by 8%. That is our rate. But we can't use a percent. We would have to change it to a decimal, which from a percent to a decimal, you move the decimal place left 2 spots. So what's right there? Now it's right there. This is 0.20, or just 0.2. If the car originally costs, that's like initially. So this would be P or N naught. I'll try to use the new formula this time. N naught was our original amount. Find the value of the car at the end of 2 years. T is 2 years. And it does say depreciates 20% per year. So these units line up, and that's good. So our final value at the end of 2 years is N. N naught is our initial value. So 20,000 times 1. And then it's depreciating. So instead, scroll up here for a second, instead of being plus R, that would be, if we had plus R, it would be R is 0.2, 1 plus 0.2. That's basically growing at 20% per year. But depreciates means losing value. So instead of plus, we have to have a minus here, 0.2, and then raised to the second power. Second power is just years, so we're gonna take basically 20% off per year. And instead of thinking of it as 20% off, we could simplify the parentheses and say that's really keeping 80% of the value. Keeping 80% and losing 20% is the same. It's the same way of saying it. So I'll go to Desmos and just type this in quick. Desmos is your friend. 20,000, 1 minus 0.2, and raise to the second power. So after 2 years of losing 20% each year, we end up with 12,800. And this is a typical case. It's kind of generalized, but it's a typical case where you drive a car off the lot, you bought it for $20,000, and then you keep it for 2 years, assuming nothing major happens to it, just regular depreciation, and it's still in good working order and everything. It's still going to be only worth $12,800, even if you didn't, even if if it just sat in your driveway and you didn't drive it, and you kept up maintenance. So it does. Big ticket items like that do depreciate in value. We could graph this function using Desmos and place a screenshot that would look like this. Let's just say I'm graphing, I'll use y equals, and then instead of 2, I'm going to change it to x. Okay, so we see the graph of this, and maybe we want to zoom in a little bit. Next is, if a city's population is 22,750, and the average growth rate is 7.5% per year, what's the city's population in 10 years? It does say per year. So this is the same situation. We could use n. N is the final amount is equal to the initial amount, 1 plus, and now this would be 2 decimal places is 0.075 raised to the 10th power. This will tell you it is growth, so we should expect our number to go bigger, and that's also the reason why there's a plus here and not a minus, because it's growing. If it was a population decay, not like rotting, but like population decreasing, then it would be a subtraction sign. So 22, 750, 1 plus 0.075 raised to the 10th power. We have 46,888. And when we're talking about populations, we typically we just kind of disregard the decimals. And it was 44, 46, 88. So that's a pretty big increase in 10 years. All right, a couple more examples. How much money should a person invest now in a money market account if you want $9,000 in the account at the end of 10 years, assuming APR 6% is 6%, compound quarterly? There's a lot of information here that we kind of need to sift through. We want this as our final amount. So this is money. I'm going to use A for this. That's our final amount. It's not P, our initial amount, or N naught. We're looking for how much we should invest. So that would be something we don't know. This is 9,000 equals P. We're solving for that. And then we have a compound interest. We have compounded quarterly. Quarterly happens 4 times a year. That means N is 4. We are going to have this $9,000 after it's been there for 10 years. So T equals 10. And then our annual percentage rate, that's what APR is 0.06. 6%, but as a decimal is 0.06. So this is the compound, because it says compound quarterly, we have to use the compound formula. 1 plus 0.06 divided by 4 raised to the nt power. So n appears again, 4 times 10 power. And this might take a second to solve because our variable is not by itself. We actually have to get it by itself. Thankfully, what's happening to our variable in order to get it by itself is we would just need to divide both sides by whatever is being multiplied to p. And what's being multiplied to p is this chunk. So if I know what that chunk is, I could just divide 9,000 by that. You could calculate what this is first and then rewrite it. But I am just going to divide by what I boxed as the green thing. So, it's 1 plus 0.06 divided by 4. And this is kind of a sneaky way to do it. 4 times 10 is 40. Sneaky way to do it because I should probably simplify this to get it to one number and then divide it. But my calculator is going to do it anyway, so I'm just going to have my calculator do it all at once. So this would be the same thing, 1 plus 0.06 divided by 4 to the 40th power. So that's all I have to type in there. 9,000 divided by, parentheses, 1 plus 0.06 divided by 4. I'm going to end the parentheses, but then raise it to the 40th power. And I get 4,961. What this means is that if I have a plan, and we typically can't see the future, but if you had a reasonable conclusion that you were going to get 6% in a compounded quarterly account, and you're going to let it sit there for 10 years, and you wanted $9,000 in 10 years, you would have to put in almost $5,000 right now, which is not that bad. I mean, if you can double your money in 10 years, that's great. If that was very consistent, everyone would do it all the time, assuming you had $5,000. Another situation, and this will be the last example, is substances being eliminated from our bodies. Let's say at a percent rate. Caffeine is eliminated from the bloodstream of an adult at about 15% per hour. After drinking cola, the bloodstream reached a peak level of 30 milligrams. Predict the amount to the nearest thousandth of a milligram remaining after 1 hour at a peak level and 4 hours at a peak level. So this isn't meant to be confusing. It's just asking you to do it twice. Once what the caffeine in milligrams is after 1 hour, and then also what it would be after 4 hours. Okay. Key thing to tell us what formula that we're going to use is that it's being eliminated by a percent. Notice you do not see the word compounded in here at all. And the fact that we have percent tells us it's not the basic one, like doubling or halving. So we would say that we don't know what the ending amount is, but we know that it starts at 30 milligrams. And then it's eliminated, so 1 minus 0.15, that's 15% as a decimal. And then after 1 hour, we would just have 1 as an exponent. Second situation is the exact same. We don't change the initial amount. It's still the initial amount. And it's nice because we can use the exact same formula and just change the amount of hours that goes by to figure out how much is there after 4 hours. So we will do this twice. 30, 1 minus 0.15 raised to the first power. And copy that and paste it and do fourth power. That's how much is there after 4 hours. So after 1 hour, at a 15% decrease, which is the same as keeping 85% of it, we have 25.5 milligrams of caffeine in our bloodstream. Well, after 4 hours, you can see that you've taken 85% of 30, and then 85% of the next amount, and then 85% of the next amount, and then 85% of the next amount. That was 4 times. And that's ends up with 15.7. All right. So again, I'll write this just right here. There were a few formulas, and one of them was y equals a times b to the x. That's the basic exponential formula. We had, I'll write the a one this time. A equals p1 plus or minus r to the t power. This is also basic by a percent, and then, or a rate, and then we also had compounded. Okay, in the next video, we'll see the other compounded formula that does not look like these necessarily, but it is also compounded continuously. All right, I hope this video helped, and good luck.